You are asking the wrong question. Not because the question is stupid, it is one of the most intelligent questions you can ask about the physical world. The kind of question that looks simple on the surface and turns out to be a window into the deepest structure of reality. But the question is phrased, contains an assumption so deeply embedded that most people never notice it. The assumption is that heat moves the way light does, that if the sun is blazing, the space around it should be warm the way a room is warm when you leave the oven on. That assumption is wrong. And understanding exactly why it is wrong will change how you think about temperature, about energy, about the relationship between matter and the void, and about the nature of heat itself, which is not what most people think it is. If you enjoy videos that start with a simple question and end somewhere you did not expect, somewhere that makes the ordinary world look stranger and more precise than it did before, I would genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let us begin. Here is the assumption buried in the question. When you ask why space is cold when the sun is so hot, you are assuming that coldness and hotness are properties of regions of space, that they are things that space can have, the way a room can be warm or a refrigerator can be cold. You are imagining space the way you imagine a room, as a container with a temperature, a place where heat distributes itself until everything inside reaches the same temperature. You walk into your kitchen on a cold morning. The room is cold. You turn on the oven. The room warms up. Heat spreads. Everything equilibrates. That is the mental model you are carrying. And it is completely, fundamentally wrong for the vacuum of space. The reason it is wrong tells you something foundational about what temperature actually is. Temperature is not a property of a region. Temperature is a property of matter. Specifically, it is a measure of the average kinetic energy of the particles in a material, the average energy of their random thermal motion. When a physicist says a gas is at 300 Kelvin, they mean that the molecules of that gas are moving randomly, bouncing off each other, vibrating and rotating, with an average kinetic energy that corresponds precisely to 300 Kelvin on the thermodynamic temperature scale. When a metallurgist says a steel rod is at 1000 Kelvin, they mean that the iron and carbon atoms locked in the metal's crystal lattice are vibrating with an average energy corresponding to 1000 Kelvin. The temperature is in the particles. It is carried by the particles. It is defined by the particles. Temperature is always a statement about matter. It is always a statement about particles, atoms, molecules, things that exist in space, things that can move and collide and carry kinetic energy. Temperature is never a statement about space itself. And here is the critical fact. Space, the vacuum between objects in the universe, contains almost no particles at all. The interplanetary medium, the region between planets in our solar system, contains roughly 5 to 10 particles per cubic centimetre. That sounds like something. 5 particles, 10 particles. You could imagine counting them. But compare it to the air in the room where you are sitting right now, which contains approximately 2.7 times 10 to the 19th molecules per cubic centimetre. That is 27 million trillion molecules per cubic centimetre. Where your air has 27 million trillion particles, interplanetary space has 5. The density difference is so vast that it strains the imagination. If you took all the air in a 1 centimetre cube of your room and spread it out until its density matched that of interplanetary space, that single cubic centimetre of air would fill a volume larger than the Earth. The interstellar medium, the space between stars in our galaxy, is even more rarefied. Typically, about 1 particle per cubic centimetre in the denser regions, dropping to fractions of a particle per cubic centimetre in the voids between the spiral arms. And the intergalactic medium, the space between galaxies, is sparser still, an almost perfect vacuum by any reasonable measure, with densities approaching 1 particle per several cubic meters. With essentially no matter in it, space cannot have a temperature in the conventional sense. There is nothing there to be hot or cold. There are no particles whose average kinetic energy you could measure. The vacuum is not cold, it is not hot. It is, in the most precise physical sense, temperatureless, a state that is fundamentally different from cold, the same way that silence is different from a quiet sound. Silence is not a quiet sound, it is the absence of sound. The vacuum is not a cold place, it is the absence of the stuff that makes a place capable of having a temperature at all. This is the first answer to the question, and it is the most fundamental one. Space is not cold. Space has no temperature. The question contains a false premise. The something you're asking about, space, is not cold. It is empty. An emptiness, in the thermodynamic sense, is not a temperature. It is the absence of temperature. But this answer, while correct, is incomplete. Because if you put a thermometer in space, if you take a physical object and place it far from any planetary body in the middle of the interplanetary medium, that thermometer will eventually reach an equilibrium temperature. It will read something, and what it reads will be very cold, about 2.7 Kelvin in the most remote regions of the universe, which is minus 270 degrees Celsius, just barely above absolute zero. So even though space itself has no temperature, objects placed in space reach very cold equilibrium temperatures. The original question is not resolved by the first answer, it is transformed. The question becomes, why do objects in space become so cold? To understand this, you need to understand the 3 mechanisms by which heat transfers between objects, the 3 channels through which thermal energy moves from one place to another. You need to understand them because 2 of these 3 mechanisms are completely absent in the vacuum of space, and the one that remains operates in a way that almost no one intuits correctly. And it is in the specifics of that remaining mechanism that the deepest answer lives. Let us start with conduction. Conduction is the transfer of heat through direct contact between particles. When you hold a metal spoon in hot soup, the energetic molecules of the hot soup collide with the metal atoms at the spoon's surface. Each collision transfers a small amount of kinetic energy from the soup molecules to the surface atoms of the spoon. Those surface atoms, now vibrating faster, collide with the atoms adjacent to them in the metal lattice, passing energy along. The energy moves atom by atom, collision by collision, from the hot end of the spoon to the cold handle. This is conduction. It is intimate, particle to particle, a relay race of kinetic energy through matter. Conduction requires physical contact between particles. It requires a medium, a continuous chain of particles through which collisions can propagate. In the vacuum of space, that medium does not exist. There are essentially no particles. The chain is broken at the very first link. If you placed a glowing hot piece of metal in the vacuum of space, none of its heat would be conducted away to the surrounding space, because there is nothing surrounding it. No chain of particles to absorb and relay the energy. The heat cannot leave the object through conduction because there is no medium for conduction to use. Now, convection. Convection is the transfer of heat through the bulk movement of a fluid. This is the mechanism you see in a pot of boiling water. Hot water rises from the bottom. Cooler water sinks to take its place, and a churning circulation develops that eventually brings the entire pot to boiling temperature. It is also the mechanism that warms your living room. Hot air from the radiator rises because heat has expanded it, making it less dense than the surrounding cool air. Gravity pulls the denser cool air down. The hot air rises, the cool air sinks, and a convection current circulates through the room, eventually bringing the entire room to thermal equilibrium. Convection requires a fluid, a medium that can flow. Gases and liquids can convect. Solids cannot, and vacuum, which contains no fluid at all, absolutely cannot convect. There is nothing to circulate. There is no medium whose density can vary, no substance that gravity can sort by density, no fluid that can carry bulk energy from one place to another. Convection is completely impossible in the vacuum of space. Remove conduction and convection, and you have removed the two mechanisms by which heat moves in almost every everyday experience you have ever had. The warmth you feel from a hot shower, the way a cold winter wind chills you, the way a cup of coffee cools on your desk, the way a fever spreads warmth through your body. All of that, conduction and convection. All of it impossible in vacuum. In the sealed, particle-free environment of space, the only remaining mechanism is radiation. Radiation is the transfer of energy through electromagnetic waves, through photons. And unlike conduction and convection, radiation does not require a medium. Photons are not carried by matter. They do not need matter to propagate. They travel through vacuum as readily, as actually more readily, than they travel through any material substance, because materials can absorb and scatter photons in ways that slow them and attenuate them. The vacuum is the medium in which photons travel most freely, with nothing to block them, nothing to absorb them, nothing to scatter them. This is why the sun can warm the Earth across 150 million kilometers of near vacuum. The heat transfer is entirely radiative. Photons leave the sun's surface, travel across the void in about 8 minutes, then arrive at Earth carrying the energy that drives our weather, our climate, our biosphere, and our civilization. Not 1 watt of that energy is delivered by conduction, not 1 watt by convection. It is all radiation. Now, understanding radiation, truly understanding it, requires going to a level deeper than most treatments of this question ever reach. Because radiation is not just a third mechanism that happens to work in vacuum. Radiation is a fundamental consequence of having a temperature at all. Every object with a temperature above absolute zero, which means every object that physically exists, emits radiation continuously. This emission of photons is called thermal radiation or blackbody radiation, and it is a direct consequence of quantum mechanics applied to the interaction between charged particles and the electromagnetic field. Here is the basic mechanism. Matter is made of atoms. Atoms contain charged particles, protons and electrons. Charged particles that are accelerating, including particles that are vibrating, oscillating, or changing direction, emit electromagnetic radiation. In any material above absolute zero, the atoms are in constant thermal motion, vibrating, rotating, colliding. All those moving charges emit photons. The hotter the material, the more vigorous the motion, the more photons emitted, and the higher the energy of those photons. The cooler the material, the gentler motion, the fewer and lower energy the photons. This is a one-way street from matter to radiation, but the reverse is also true. Matter can absorb photons. When a photon strikes a material and is absorbed, its energy is transferred to the material's atoms, increasing their thermal motion, which means increasing the material's temperature. So matter and radiation are in constant dialogue. Matter emits photons, and photons are absorbed by matter. The equilibrium state, when an object's temperature is stable, is the state where the rate of emission exactly equals the rate of absorption. In space, radiation is the only channel through which this balance can be achieved. An object in space loses heat only by emitting photons. It gains heat only by absorbing photons. Its equilibrium temperature, the temperature it eventually settles to, depends entirely on the balance between those two processes. For an object far from any star, in the vast emptiness between galaxies, the only photons it receives are from the cosmic microwave background radiation. And to understand why space has the specific temperature it has, 2.725 Kelvin, not some other number, you need to understand what the cosmic microwave background actually is, because it is not just a technical detail. It is the universe's most important artifact. It is light from the beginning of time. The universe began approximately 13.8 billion years ago in an extraordinary hot, dense state. In the first fractions of a second after what we call the Big Bang, temperatures were so high, around 10 to the 32nd Kelvin, that matter, as we know it, could not exist. There were no atoms, there were no protons, there were barely any of the particles we recognize from particle physics. The universe was a plasma of fundamental constituents in a state of energy so intense that our current physics breaks down trying to describe it. The laws of nature, as we understand them, were likely different, or at least operating in regimes we have not yet mapped. As the universe expanded, it cooled. This cooling is a fundamental consequence of the expansion of space. Expansion stretches the wavelengths of radiation, and longer wavelength means lower energy per photon, which means lower temperature. In the first fractions of a second, the universe cooled through the temperatures at which quarks condensed into protons and neutrons. In the first 3 minutes, temperatures dropped through the range where nuclear fusion was possible, around 10 to the 9th Kelvin, and the light elements formed: hydrogen, helium, and traces of lithium. In proportions we can still measure today in the oldest, most pristine stars. For the next approximately 380,000 years, the universe was a hot, opaque plasma. Photons could not travel freely because they were constantly scattered by the free electrons that permeated the plasma. The universe was like the interior of the sun, dense enough that light could not escape, trapped in an endless scattering cascade. Every photon that tried to travel any significant distance was immediately deflected by the next electron it encountered. Then, at about 380,000 years after the Big Bang, something decisive happened. The temperature dropped below approximately 3000 Kelvin, the temperature at which free electrons and protons combine to form neutral hydrogen atoms. This process, called recombination, happened relatively quickly across the entire universe, and when it happened, the universe became transparent to radiation almost overnight on cosmological timescales. The free electrons that had been blocking the photons were suddenly gone, captured into atoms. For the first time in the universe's history, photons could travel freely. Those photons, the photons that had been trapped in the plasma and were suddenly liberated at the moment of recombination, streamed outward in all directions. They have been travelling freely ever since. 13.8 billion years of uninterrupted travel through the expanding universe. And during all that time, the expansion of the universe has been stretching their wavelengths. When they were released at recombination, they corresponded to a temperature of about 3000 Kelvin. They were visible light photons, glowing orange-red. Over 13.8 billion years of cosmic expansion, their wavelengths have been stretched by a factor of approximately 1,100, shifting them from visible light all the way down to microwave frequencies. Their temperature has dropped from 3000 Kelvin to 2.725 Kelvin. Those photons are the cosmic microwave background. They fill all of space uniformly in every direction at the same temperature. Wherever you are in the observable universe, you are bathed in this ancient radiation. It comes at you equally from every direction because the surface of last scattering, the spherical shell at which these photons were last scattered before release, surrounds us equally on all sides. At a distance corresponding to 13.8 billion light years, an object completely isolated from stars and other local heat sources will absorb this radiation and emit its own radiation. It will cool until emission equals absorption. Its equilibrium temperature will be 2.725 Kelvin. That is the floor. That is the lowest temperature any ordinary object in the universe can have, because the universe itself is at that temperature. You cannot radiate heat into something colder than 2.725 Kelvin, because there is nothing in this universe colder than 2.725 Kelvin. The universe's own background radiation is the thermal floor. The coldness of space is therefore not arbitrary or approximate. It is a specific, precisely measured number, 2.748, plus or minus 0.55 Kelvin, as measured by the Planck satellite, that encodes the entire thermal history of the universe from the Big Bang to the present day. It tells you how old the universe is, it tells you how much the universe is expanded, it tells you what the temperature was at the moment matter and radiation decoupled. It is one of the most precisely measured quantities in all of cosmology, and one of the most cosmologically meaningful. Think about what that precision means. We are measuring a temperature left over from an event that occurred 13.8 billion years ago, encoded in the wavelengths of photons that have been travelling freely through expanding space ever since. And we know that temperature to better than 1 part in 10,000. The universe handed us its birth certificate, written in microwave light, and we were careful enough to read it correctly. Now we need to address the apparent paradox directly. The sun is pouring an enormous amount of radiation into space, 3.8 times 10 to the 26 watts of power, that is 380 septillion watts, flowing outward from the sun's surface in every direction. The sun is one of the most powerful objects in the solar system, perhaps one of the most energetically productive objects in the immediate cosmic neighbourhood. It is radiating constantly, ferociously, relentlessly. Why does this not heat space? The answer requires understanding something about photons that is easy to miss. Photons do not heat the space they travel through. They heat only the matter they are absorbed by. A photon moving through vacuum is not depositing energy as it goes. It is not gradually leaking energy into the space around it, like a hot wire radiates heat to the surrounding air. A photon in vacuum is discrete and indivisible. A quantum of energy that exists as a whole or not at all. It travels at the speed of light, carrying its energy intact, interacting with nothing until it encounters matter capable of absorbing it. At that point, it deposits all of its energy, completely, entirely, instantaneously, into the absorbing matter. The absorber's temperature increases by exactly the amount corresponding to the energy of that photon, and the photon is gone. There is no gradual process. There is no leaking. The photon's energy is binary, absorbed here or not absorbed, until it reaches something else. If nothing absorbs it, it travels forever. The vacuum between the Sun and the planets contains essentially no matter. The 5 to 10 particles per cubic centimetre in the interplanetary medium are real. There are sparse protons and electrons and dust grains out there, but their density is so vanishingly low compared to any normal material that the interplanetary planet medium is for nearly all practical purposes perfectly transparent to electromagnetic radiation. The photons stream through it without interacting. Think of it this way. You are in a dark room. You turn on a flashlight and point it at the far wall. The beam of light crosses the room. Does the air in the room heat up because the beam passes through it? Not meaningfully. The photons in the beam are absorbed only by air molecules they directly strike, and since air is overwhelmingly transparent to visible light, essentially none of the beam's photons are absorbed by the air. They travel across the room and hit the wall. The wall absorbs them. The wall warms up. The air between you and the wall does not warm up, not because the light ignored it, but because light and air are not good at exchanging energy in this frequency range. Space is the ultimate extension of that principle. The interplanetary vacuum is millions of times more transparent to sunlight than air is, because there are millions of times fewer particles to absorb anything. The Sun's photons travel from the solar surface to the planets, passing through 150 million kilometers of vacuum, and deposit essentially none of their energy along the way. They arrive at Earth and are absorbed by the atmosphere, the oceans, the land. Earth warms. Space does not. This is why you can be simultaneously in intense sunlight and be exposed to the thermal environment of near absolute zero. The sunlit and shadowed sides of the same object in space can be at wildly different temperatures. A flat metal plate positioned perpendicular to the sun's rays at Earth's distance will reach an equilibrium temperature of around 279 Kelvin on its sunlit face because it is absorbing solar photons and emitting infrared photons. And those two rates balance at that temperature. But the shadowed face of the same plate, pointing away from the sun into deep space, is radiating infrared photons into a background at 2.725 Kelvin. It is losing heat rapidly and receiving almost none. Its temperature plummets. The temperature gradient across a thin plate in space, from the sunlit face to the shadowed face, can be hundreds of degrees Celsius across a thickness of millimeters. This is not a small engineering inconvenience. It is a fundamental engineering challenge for every spacecraft ever built, and the solutions developed to manage it reveal, in practical and observable terms, exactly the physics we have been discussing. There is another way to understand this that goes even deeper. The intensity of solar radiation follows an inverse square law. It decreases with the square of the distance from the Sun. At Earth's distance of 150 million kilometers, the solar constant, the power per unit area arriving at Earth, is approximately 1,361 watts per square meter. At Mars's distance, roughly 227 million kilometers, it falls to about 590 watts per square meter. At the distance of Saturn, about 1.4 billion kilometers, it is down to around 15 watts per square metre. At the Voyager probe's current distance of more than 23 billion kilometres, the Sun's output has diluted to less than 1/100th of a watt per square metre. The Sun's energy is real and enormous at its source, but it is spreading across an ever larger sphere of space, diluting without limit, heating nothing along the way, depositing itself only when it finally encounters matter to absorb it. When astronauts perform spacewalks, extravehicular activity, EVA in NASA parlance, they spend hours outside the space station in the vacuum of space, moving through alternating periods of direct sunlight and deep shadow as they orbit Earth. The thermal environment they operate in is precisely the environment we have been describing. Radiation is the only heat transfer mechanism. Conduction and convection do not exist, and the difference between sunlit and shadowed surfaces is extreme. The EVA suit, the full spacesuit worn during spacewalks, is an engineering solution to this problem. Its outermost layer, the thermal micrometeorite garment, is white. The choice of white is not aesthetic. White surfaces have high reflectivity in the solar spectrum, which means they reflect the majority of incoming solar photons rather than absorbing them. A white surface absorbs significantly less solar energy than a dark surface of the same size. This prevents the astronaut from overheating during sunlit portions of the orbit. But white surfaces also have specific radiated properties in the thermal infrared, the frequencies at which a warm object emits its own heat radiation. The suit's materials are chosen to balance these two requirements: low solar absorptivity to stay cool in sunlight, and controlled thermal emissivity to retain enough heat in shadow to keep the astronaut from freezing. Inside the suit, multiple layers of aluminized mylar insulation trap the astronaut's body heat during the cold shadow periods. The layers work precisely because there is no convection inside the vacuum-like interstitial spaces between them. In air, those layers would be useless. Convection currents would carry heat right through them. In the near vacuum inside the insulation layers, only radiation matters, and radiation moves poorly through multiple thin reflective layers. The International Space Station itself experiences temperature swings between about -157 degrees Celsius in shadow and about 121 degrees Celsius in full sunlight, a range of nearly 280 degrees Celsius, cycling through this range every 90 minutes as the station completes each orbit. Managing this thermal environment requires sophisticated radiators, heaters, multi-layer insulation blankets, thermal control software, and fluid loops that move heat from interior components to exterior radiator panels, where it can be emitted to space. The station's thermal control system is one of its most complex subsystems, invisible to the public but absolutely essential to every person and every experiment aboard. The James Webb Space Telescope, launched in December 2021, represents perhaps the most extreme application of radiation-only thermal management in the history of human engineering. JWST observes the universe in the infrared, wavelengths ranging from near-infrared to mid-infrared, and it does so with unprecedented sensitivity. But infrared astronomy has a fundamental problem. Anything warm emits infrared light. If the telescope's own mirrors and detectors are warm, they will flood the sensors with their own thermal glow, drowning out the faint infrared signals from distant galaxies. To avoid this, JWST must be maintained at temperatures below 50 Kelvin, colder than most of the space around it. For the mid-infrared detectors, even colder, below 7 Kelvin, requiring an active cryogenic cooling system. How do you get a telescope this cold? You cut off every source of heating, and the primary source of heating in the inner solar system is the Sun. JWST carries a sun shield, a 5-layer structure roughly the size of a tennis court, made of Kapton film coated with aluminum and silicon. This shield blocks the Sun, Earth, and Moon, the 3 dominant sources of radiation in the telescope's environment, from ever reaching the telescope side of the spacecraft. With the sun shield blocking all incoming radiation from those sources, the telescope side has no significant source of heat. It cools by emitting its own thermal radiation into the deep darkness of space. It cools toward the ambient temperature of its environment, the 2.725 Kelvin of the cosmic microwave background. The sun shield works precisely because there is no convection or conduction. In space, if you block the radiation pathway, you block the heat. There is no air to convect heat from the hot side to the cold side. There is no material conducting heat around the shield. The radiative block is a complete block. The shield's hot side, facing the sun, reaches temperatures around 85 degrees Celsius. The shield's cold side, facing the telescope, drops below minus 233 degrees Celsius. The 5 layers of the shield, each one cooler than the last, each one absorbing and emitting radiation in stages, create a thermal cascade from solar illuminated warmth to mere unsatisfactory task. Play a task. Boulder. That cascade is possible only because radiation is the sole mechanism of heat transfer, and radiation can be blocked. With an opaque shield, the Mars rovers, Curiosity and Perseverance, face a different version of the same physics. Mars is about 1.5 times farther from the Sun than Earth, receiving proportionally less solar energy. Its thin atmosphere, about 0.6% of Earth's atmospheric pressure, provides only minimal convective heat transfer. The planet's surface experiences temperature swings from about minus 80 degrees Celsius at night to about 20 degrees Celsius in the afternoon at favourable locations. Equipment designed for Earth's stable thermal environment would fail catastrophically in this regime. Curiosity's heat rejection system uses a fluid loop to move waste heat from the electronics, which generates significant heat during operation, to radiators on the rover's body that emit the heat to space as infrared radiation. In cold Martian nights, the same system conserves heat by circulating warm fluid to maintain minimum operating temperatures. The radioisotope thermoelectric generator that powers Curiosity also produces significant waste heat, which the thermal control system carefully routes to keep electronics warm during the deep cold of Martian nights. Every detail, the colour and finish of each panel, the thickness of insulation around each component, the path of each fluid loop, reflects a detailed accounting of the radiation budget. The Voyager probes, Voyager 1 and Voyager 2, launched in 1977, represent the ultimate endpoint of this engineering challenge. Both probes are now in the interstellar medium, beyond the heliopause, the boundary where the Sun's solar wind can no longer push back the interstellar medium. Voyager 1 is currently more than 23 billion kilometers from the Sun. At that distance, the intensity of solar radiation is roughly 30,000 times weaker than at Earth's distance. The Sun is not a meaningful heat source at that distance. It is barely brighter than the other stars. The Voyager probes are kept operational by their radioisotope thermoelectric generators, which convert the heat from the radioactive decay of plutonium-238 into electricity. Plutonium-2038 has a half-life of approximately 87.7 years, which means the power output has been declining continuously since 1977. Approximately 47 years after launch, the generators are producing roughly half the power they did at launch. The Voyager team has been responding to this by systematically deactivating instruments and heaters that can no longer be supported, extending the mission's useful life by ruthlessly prioritizing the remaining power. Without adequate heating, scientific instruments reach temperatures at which their electronics fail. The thermal environment the probes must survive, with radiation as the only heat transfer mechanism, and the ambient temperature of the interstellar medium at about 2.725 Kelvin, means that any component without an active heater will cool toward absolute zero. When the probes finally go silent, they will continue traveling through interstellar space indefinitely, cooling toward the CMB temperature as their residual warmth slowly radiates away. They will approach 2.725 Kelvin asymptotically, getting closer and closer but never quite reaching it, because the rate of cooling slows as the temperature differential narrows. To go deeper, and we are going deeper, we need to understand the physics of why hot objects glow, and why this was such a profound mystery in the late 19th century that it required the invention of an entirely new branch of physics to solve. Because the solution to that mystery is directly embedded in the reason space is cold. The two are not separate topics, they are the same topic. By the 1890s, physics had achieved enormous successes. Newton's mechanics had been extended and refined for 2 centuries. Maxwell had unified electricity, magnetism, and light into a single theoretical framework, electromagnetism, and predicted the existence of radio waves, which Hertz had immediately confirmed experimentally. Thermodynamics had been established on rigorous foundations, with the kinetic theory of gases explaining temperature and pressure in terms of molecular motion. The periodic table had been assembled. Spectroscopy had revealed that different elements produced different characteristic spectra. Physics seemed on the verge of being complete. But there was a problem with thermal radiation, with the light that had maybe sent out to move or to send it to work. The problem was, to use the technical term that physicists coined for it, the ultraviolet catastrophe. Classical physics predicted, rigorously, unavoidably, from well-established principles, that a hot object should emit infinite energy at short wavelengths. The argument went like this: according to classical electromagnetism and classical statistical mechanics, each mode of oscillation in the electromagnetic field should carry, on average, an energy proportional to temperature. The number of electromagnetic modes per unit frequency increases without limit as frequency increases. Multiply the number of modes by the energy per mode, and you get the total energy at each frequency, and that product diverges at high frequencies. The prediction is infinite radiation at ultraviolet and shorter wavelengths. Infinite power. An obvious and catastrophic wrong answer. But hot objects do not emit infinite energy. They emit a specific spectrum. A steel ingot heated in a furnace glows red, then orange, then yellow-white as its temperature increases. A star at 3000 Kelvin glows red. A star at 10,000 Kelvin glows blue-white. The spectrum is always a smooth curve, peaking at a specific wavelength that shifts with temperature, and falling off on both sides, especially falling off sharply at high frequencies. The ultraviolet catastrophe did not happen in reality. Classical physics predicted it anyway. Something was fundamentally wrong. The resolution came in October 1900, when Max Planck, a meticulous German physicist who had spent years trying to understand the thermal radiation spectrum empirically, proposed a mathematical formula that fit the experimental data perfectly. His formula contained a new constant, now called Planck's constant, h, and it described the spectrum with accuracy that previous attempts had never achieved. But Planck did not initially understand what his formula was physically saying. He worked backward from the formula to find the assumption that would produce it, and what he found disturbed him. The assumption was this: energy is not continuous. It comes in discrete, indivisible chunks, quanta. Specifically, the electromagnetic field can only exchange energy with matter in units of hf, where h is Planck's constant and f is the frequency of the radiation. You cannot add or remove half a quantum. You can only add or remove whole quanta. Energy, at the microscopic level, is granular. This was a radical, almost shocking proposal. Classical physics assumed energy was a continuous quantity. You could add or remove any amount, however small. Planck's quantum hypothesis shattered that assumption, and once it was in place, the ultraviolet catastrophe was resolved automatically. High-frequency radiation, ultraviolet, X-rays, gamma rays, requires high-energy quanta to excite each electromagnetic mode. At ordinary temperatures, the thermal energy available, the energy in the thermal jiggling of atoms, is simply not enough to supply high-energy quanta to many high-frequency modes. Those modes go unexcited. The emission at high frequencies is suppressed, not because anything is preventing it in principle, but because the thermal energy available is insufficient to purchase high-frequency quanta at Planck's price. The spectrum has a natural cutoff at high frequencies, not infinite, but finite, smooth, and precisely matching what experiments had always shown. Planck himself described his own discovery with characteristic ambivalence. He called the quantum hypothesis an act of desperation. He had tried every classical approach he knew and failed. The quantum was not something he chose, it was something the data forced on him. He spent years afterward trying to find a way to derive his formula without the quantum assumption, trying to reabsorb the strange new idea back into classical physics. He failed. The quantum was real. The universe was granular at the bottom. Planck's insight was the first step in the quantum revolution. Einstein extended it in 1905, proposing that light itself is quantized, that electromagnetic radiation is not a continuous wave, but is composed of discrete photons, each with energy h, f. Bohr applied quantum ideas to the atom. Heisenberg, Schrödinger, Dirac, and others built the full mathematical framework of quantum mechanics in the 1920s. The result was a complete reconstruction of our understanding of matter and energy at the microscopic scale, a reconstruction so profound that it underlies all modern technology, from transistors to lasers to MRI machines to the solar panels on the International Space Station. And it is directly relevant to why space is cold. The quantization of radiation is why the cosmic microwave background has the specific temperature it has. The CMB spectrum is a perfect blackbody spectrum, a perfect Planck curve with no deviations that have ever been detected within measurement precision. When the COB satellite measured the CMB spectrum in 1992, it found a Planck curve so perfect that the theoretical prediction and the experimental measurement were indistinguishable on the graph. John Mather won the Nobel Prize in Physics, partly for that measurement, because it was the most precise measurement of a blackbody spectrum ever made, and because the perfection of that spectrum told an entire story about the history of the universe. There is another piece of thermal radiation physics that is essential to understanding the behavior of objects in space, the Stefan Boltzmann law. This law describes the total power radiated by an object as a function of its temperature. And it is not a linear relationship. It is not even a quadratic relationship. The power radiated is proportional to the fourth power of the temperature. If you double an object's temperature, it radiates not twice as much power, not 4 times as much, but 16 times as much. Temperature to the fourth power. Quadruple the temperature, the power increases by a factor of 256 times. The relationship is extremely steep. This has profound consequences for objects in space. Consider an object warming up in sunlight. As its temperature rises, it radiates energy at an ever-increasing rate. The hotter it gets, the faster it radiates. This creates a powerful self-stabilizing mechanism. As the object heats up toward its equilibrium temperature, the rate of radiative heat loss accelerates rapidly, countering the heat input and pulling the temperature back toward equilibrium. The equilibrium temperature is stable and well-defined because of the fourth power steepness of the radiation law. Now, consider the reverse, an object cooling in the dark. As it cools, the rate at which it radiates decreases. The colder it gets, the more slowly it loses heat. The cooling rate is not constant. It slows dramatically as the temperature drops. An object cooling from 100 Kelvin to 90 Kelvin loses heat 10 times faster than the same object cooling from 10 Kelvin to 9 Kelvin. The last few degrees above absolute zero are extraordinarily difficult to shed. This is why the Voyager probes, when they eventually lose their power sources, will cool slowly toward the CMB temperature rather than rapidly. It is why deep space telescopes that need to reach very low temperatures require active cooling systems. Passive radiative cooling is too slow and too limited once you get to temperatures near the CMB floor. It is why cryogenic engineering for space-based infrared telescopes like JWST is such a formidable challenge. The Stefan-Boltzmann law also explains something about the Sun that is worth dwelling on. The Sun's surface temperature of 5,778 Kelvin produces a luminosity, a total power output of 3.828 times 10 to the 26th watts. That number is called the solar luminosity, and it is one of the fundamental constants of astrophysics. Every element of that number flows from the Stefan-Boltzmann law applied to the Sun's surface area and temperature. If the Sun was slightly cooler, say 5,000 Kelvin, instead of 5,778, it would radiate significantly less power per unit area, and Earth would be significantly colder. The relationship between stellar temperature and planetary habitability runs directly through the fourth power radiation law. The same law governs what happens when the Sun's light reaches Earth. Earth absorbs solar radiation and must emit the same amount back to space at thermal equilibrium. The absorbed solar power and the emitted thermal power must be equal. Earth's average temperature adjusts until this balance is achieved. The calculation gives a predicted equilibrium temperature that is somewhat lower than Earth's actual average temperature. The difference is the greenhouse effect, caused by the atmosphere's absorption of outgoing infrared radiation. But the basic principle is pure Stefan Boltzmann. The planet's temperature adjusts until it is radiating exactly as much energy as it receives. There is something beautifully mechanical about this self-regulation. Earth does not have a thermostat in the engineering sense. It has no sensor measuring temperature and no actuator adjusting output, and yet it self-regulates its temperature automatically through the physics of the fourth power law. If the Sun's output increases slightly, Earth absorbs more energy and warms slightly, but even a small warming causes a large increase in Earth's radiative output because of the fourth power, which rapidly restores the balance. The planet is thermally stable because the law of radiation is so steep. Without the fourth power relationship, planetary temperatures would be far less stable. Life would face a much more volatile thermal environment. Now I want to pull back to the larger scale and see the full picture, because the sun being hot and space being cold are not independent facts that happen to coexist. They are causally connected in a way that illuminates not just astrophysics, but the nature of complexity and life in the universe. The universe, as we noted, began in an extraordinarily hot, dense state. In those first moments, the universe was hot, everywhere, uniformly hot. There was no temperature gradient, there were no cool regions and hot regions. There was just heat, distributed everywhere at the same extreme temperature. As the universe expanded, it cooled. The cooling was uniform, every region of the universe cooled together, because the universe was, to a very high degree of approximation, homogeneous and isotropic. The same temperature everywhere, cooling together. In those early epochs, there was no thermodynamic gradient available. No hot regions and cold regions, no way to extract useful work from temperature differences. And therefore, although the chemistry of the early universe was rich in some ways, there was no possibility of the kind of hierarchical complexity that eventually produces planets, biospheres, and minds. Gravity changed this. Small density fluctuations in the early universe, tiny regions that were very slightly denser than their surroundings, grew under gravitational attraction. Matter fell into those overdense regions. As it fell, gravitational potential energy converted to kinetic energy, and kinetic energy converted to thermal energy. The collapsing regions heated up while their surroundings stayed cool. For the first time in the universe's history, there were hotspots, dense concentrations of matter much hotter than their surroundings. Those hotspots emitted as stars. The first stars formed a few 100 million years after the Big Bang, in an epoch we call cosmic dawn, when the universe transitioned from a dark, uniformly cool sea of hydrogen and helium to a cosmos punctuated by blazing stellar fires. Each star was a gravitational machine, using gravity to compress hydrogen to the temperatures required for nuclear fusion, then using fusion to sustain itself against further gravitational collapse, radiating energy in all directions as it burned. The universe today is structured as it always has been, since cosmic dawn, an ocean of cold, the 2.725 Kelvin of the CMB, decreasing slowly as the universe continues to expand, punctuated by isolated islands of heat, the stars. The stars are the temperature gradient. They are the thermodynamic inequality that makes complexity possible. Without them, the universe would be a cold, dark, undifferentiated expanse, cooling toward absolute zero as the CMB temperature falls. With them, there are local hotspots, temperatures of thousands to millions of Kelvin, embedded in a cold background, and wherever there is a temperature gradient, thermodynamics permits work to be extracted. Wherever work can be extracted, organized, self-sustaining processes can arise. Wherever organized processes can arise and persist for long periods, complexity can accumulate. Life is complexity that arose at the interface between a hotspot and the cold background. We exist on a planet that is close enough to a star to receive meaningful energy, enough to drive chemistry, evaporate water, fuel weather, and far enough from the star that we are not destroyed by its intensity. We are at the right distance that liquid water can exist on our surface. We are in the Goldilocks zone, the habitable zone, the circumstellar region where stellar radiation is neither too intense nor too faint to permit the chemistry of life. But the habitable zone is defined not just by the star, it is defined by the contrast between the star and space. If space were not cold, if the CMB were at, say, 500 Kelvin instead of 2.75 Kelvin, the universe would be a very different thermodynamic environment. The temperature contrast between the sun and its surroundings would be much smaller. The capacity to radiate heat away from a planet would be much reduced. The planet's equilibrium temperature would be much higher. Life as we know it, life that depends on specific temperature ranges and specific thermodynamic gradients, would be impossible. The coldness of space is not a hazard for life. It is one of the conditions for it. Let us develop this point carefully, because it is the deepest answer to the original question, and it is the one that most people never reach. Thermodynamics, the branch of physics dealing with heat, energy, and their interconversions, has 4 fundamental laws. The most famous is the second law. Entropy, a measure of disorder, never decreases in a closed system. Heat flows spontaneously from hot to cold, never the reverse. Order spontaneously becomes disorder, never the reverse. The universe moves inexorably towards states of higher entropy. But there is a way to locally decrease entropy, to locally create order without violating the second law. You can decrease entropy in one place if you increase it by a larger amount elsewhere. A refrigerator creates cold inside itself, decreasing entropy. By dumping heat outside, increasing entropy by more. The net entropy of the system plus surroundings still increases. The second law is satisfied. Local order is purchased at the price of global disorder. Life does exactly this. A living organism is a highly ordered, low entropy structure, incredibly improbable, incredibly organized, maintained against the constant thermodynamic pressure toward disorder. It maintains itself by consuming high-quality energy from its environment and expelling low-quality energy as waste heat. The high-quality energy is photons from the sun, high-energy photons at 5,778 Kelvin, carrying concentrated, organized energy. The low-quality waste is infrared photons emitted at around 310 Kelvin, body temperature, carrying dispersed, degraded energy. The difference, the gap in entropy between the high-quality input and the low-quality output, is what the organism uses to maintain its structure, reproduce, and do everything we recognize as living. Plants are the most direct example. A plant absorbs a photon from the sun, a photon carrying energy corresponding to the sun's 5,778 Kelvin surface temperature. It uses the energy of that photon to drive a chemical reaction, the synthesis of glucose from carbon dioxide and water. The glucose stores the energy in chemical bonds. The plant has, at the cost of that single high-energy photon, produced a molecule of structured, chemically complex fuel. It has locally decreased entropy. Meanwhile, it re-emits lower-energy photons, infrared photons, at around 300 Kelvin to balance its radiation budget. The photons it emits carry less energy per photon and more entropy per unit of energy than the photons it absorbed. Def. No satellite photons are often low. The net entropy of the universe increases. The second law is satisfied. Life persists. An animal eating a plant extends this chain. The animal's metabolism burns the chemical energy stored by the plant, releasing it as body heat, infrared radiation emitted at body temperature, while using the energy gradient to drive the synthesis of complex molecules, maintain cellular structure, power muscle contraction, and propagate nerve signals. Every heartbeat, every thought, every movement is thermodynamically powered by the temperature gradient between the sun and space. Now consider what happens if you remove the cold sink. Suppose space were at the same temperature as the sun, 5,778 Kelvin everywhere. Then the sun would not be emitting photons net, it would be receiving as many photons as it emits, because the surroundings are at the same temperature. There would be no net energy flow, no photosynthesis, no metabolism, no life. Or suppose space were at room temperature, 300 Kelvin everywhere. Then the sun, at 5,778 Kelvin, would still radiate more than it receives, and energy would flow from sun to planet. But the planet could not radiate this energy away, because the environment it would be radiating into is at 300 Kelvin, not 2.75 Kelvin. The planet would heat up. It could not liberate at a life-friendly temperature. The thermodynamic engine would be degraded. The specific temperature of the cosmic microwave background, 2.725 Kelvin, is what it is because of the age and expansion history of the universe. We happen to exist at a time and in a universe where the CMB temperature is low enough and stellar temperatures are high enough that the thermodynamic contrast is enormous. More than 2,000 to 1 in temperature, corresponding to a vastly larger ratio in free energy per photon. That contrast is the thermodynamic engine of the biosphere. The window of time in which this engine operates is bounded. Earlier in the universe's history, before the first stars formed, in the first few 100 million years after the Big Bang, there was no temperature gradient. The universe was still warm from the Big Bang, cooling, but not yet differentiated into stars and voids. Life could not arise. There were no local hotspots, no planetary systems forming around them, no stable chemical environments maintained by stellar energy. The universe was too young, too uniform, too undifferentiated. Later in the universe's history, trillions of years from now, after the last stars have burned out, there will again be no temperature gradient. The last red dwarf stars will exhaust their hydrogen fuel in roughly 100 trillion years, about 7,000 times the current age of the universe. After that, no new stars will form. The universe will contain only stellar remnants, white dwarfs slowly cooling, neutron stars slowly cooling, black holes slowly evaporating via Hawking radiation. The CMB temperature will itself continue to drop as the universe expands, eventually reaching temperatures so close to absolute zero that there is no meaningful distinction. The universe will approach a state of maximum entropy, heat death, where everything is at the same vanishingly small temperature and no thermodynamic gradient exists anywhere, no free energy, no way to do work, no complexity, no life. Between these two sterile epochs, the hot, undifferentiated youth and the cold, exhausted old age, there is a window, the stelliferous era, the epoch of stars. We are in it. We are approximately 13.8 billion years into a window that will close in roughly 100 trillion years. On that time scale, we are early. The universe is young by comparison to the full span of stellar existence, and the stars are at their most numerous and most active. The thermodynamic engine is running at high efficiency. The fact that you are asking this question, the fact that you exist as a mind capable of formulating questions about cosmology and thermodynamics, is itself a consequence of being in this window. The human brain the most thermodynamically expensive object per unit mass in the known biosphere, consuming roughly 20% of the body's energy budget, despite comprising only 2% of its mass, is an extraordinarily concentrated thermodynamic structure. It arose because the thermodynamic engine of the biosphere could sustain it, because photosynthesis could capture enough energy from stellar radiation to build the food webs that support large energy-hungry brains. It would not have arisen if the thermodynamic gradient were not large. It will not persist if the gradient disappears. You are asking why space is cold when the sun is hot. The deepest answer is that you are asking the question from inside the temperature gradient. You are the consequence of the gradient. We have been talking about the cosmic microwave background as if it were perfectly uniform, 2.725 Kelvin everywhere you look in the sky, in every direction, without variation. As to an extraordinary degree, that is true. We have to prove that this affects. If you point a microwave detector at any part of the sky, you'll measure 2.725 Kelvin. Point it somewhere else, any direction, still 2.725 Kelvin. The uniformity is remarkable, and it is one of the most important facts about the universe. But not quite perfectly uniform. In 1992, the SOBE satellite, the Cosmic Background Explorer, detected for the first time tiny temperature variations in the CMB, fluctuations of approximately 1 part in 100,000. Across the entire sky, there are regions that are very slightly hotter than average, perhaps 2.7253 Kelvin, and regions that are very slightly cooler, perhaps 2.7247 Kelvin. The differences are real, measured, cosmologically significant, and impossibly small by any everyday standard. These tiny fluctuations are not random noise. They are not measurement artifacts. They are the fossil record of quantum fluctuations in the very early universe, density variations that were imprinted on the universe during a period called cosmic inflation, an epoch of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang. During inflation, quantum scale variations in the energy density of the universe were blown up to cosmological scales. Those variations became the seeds of structure, the slightly overdense regions that eventually collapsed under gravity to form galaxies, galaxy clusters, the cosmic web. The pattern of temperature fluctuations in the CMB, the specific sizes, shapes, and statistical distribution of the hot and cold spots, is an extraordinarily precise diagnostic of the universe's composition, geometry, age, and expansion history. By measuring this pattern with exquisite precision, cosmologists have been able to determine that the universe is 13.8 billion years old, that it is spatially flat to within measurement error, that it contains approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, and that it began with an inflationary epoch that lasted from roughly 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang. All of that, the entire standard cosmological model, with its extraordinary precision, is written in temperature variations of 1 part in 100,000 across the cold microwave sky. The universe's autobiography is encoded in the fine structure of its coldness. There is something profoundly strange and beautiful about this. The coldest, most diffuse radiation in the universe, the photons left over from 380,000 years after the Big Bang, now stretched to microwave frequencies. Arriving from all directions with a temperature barely above absolute zero, carries more precise cosmological information than almost any other observable. The faintest signal in the sky turns out to be one of the loudest voices telling us who we are and where we came from. The WMA satellite, launched in 2001, mapped the CMB fluctuations with far greater precision than COBE. The Planck satellite, launched in 2009 and operating until 2013, mapped them with still greater precision, achieving angular resolution and sensitivity that allowed cosmologists to distinguish features in the CMB pattern corresponding to acoustic oscillations in the primordial plasma, the pressure waves that propagated through the hot plasma in the first 380,000 years, like sound waves in an extraordinarily hot, dense gas. Those acoustic peaks in the CMB power spectrum, the specific angular scales at which the temperature fluctuations are enhanced, are the frozen record of sound waves that propagated through the early universe and were suddenly stopped, frozen in place when recombination happened and the universe became transparent. The characteristic angular scale of those peaks tells you the distance sound could travel in the first 380,000 years, the acoustic horizon, which depends on the speed of sound in the primordial plasma, and the age of the universe at recombination. By measuring where those peaks fall in the CMB spectrum, cosmologists can reconstruct the composition of the early universe with extraordinary precision. The coldness of space, measured in microscopic detail, yields a complete census of the universe's contents. This is perhaps the most counterintuitive thing about the coldness of space. The cold is not empty of information. The cold is saturated with information. Every photon in the cosmic microwave background carries, encoded in its frequency and direction, a message from the beginning of time. The universe's cold is not silence. It is a voice speaking from the moment of its own birth, and we have learned, over the last 3 decades, to listen to it with remarkable precision. We have talked about 2.725 Kelvin as the floor of temperature in the universe, the coldest anything can get, because the universe itself is at that temperature, and you cannot radiate heat into something colder than yourself. But this raises a question that we have been circling without answering. What is absolute zero, really? What does it mean to say that temperature cannot go below 0 Kelvin? And is the prohibition absolute? Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, is the temperature at which the average kinetic energy of particles reaches its minimum possible value. In a classical picture, this would mean all particles are perfectly still, all thermal motion has ceased, all randomness has been extracted. But quantum mechanics complicates this picture in an important and interesting way. Quantum mechanics forbids particles from being perfectly still. The Heisenberg uncertainty principle states that you cannot simultaneously know the position and momentum of a particle with perfect precision. If a particle were perfectly still, if its momentum were exactly 0, then you would know its momentum with perfect precision. But the uncertainty principle forbids this. Perfect knowledge of momentum requires complete ignorance of position, and vice versa. In practice, particles always have a residual, irreducible quantum motion, even at absolute 0. This is called zero-point energy, and it is a real, measurable phenomenon. Helium-4, the most abundant isotope of helium, is the only substance that remains liquid at atmospheric pressure all the way to absolute 0, precisely because of zero-point motion. Every other substance freezes into a solid as temperature drops. The thermal motion that keeps molecules separated decreases. The attractive forces between molecules win, and the substance solidifies. But helium's zero-point motion is large enough, because helium atoms are light enough, that even at absolute zero, the atoms are still jiggling enough to prevent solidification. Helium remains liquid at absolute zero unless you apply pressure. The zero-point motion of quantum mechanics literally keeps it fluid against the force of cooling. So absolute zero is not the temperature at which all motion stops. It is the temperature at which all thermal motion, all motion above and beyond the irreducible quantum minimum, has been removed. The quantum floor remains. Now, can you reach absolute zero? The third law of thermodynamics says you cannot, not in a finite number of steps. To cool something to absolute zero, you would need to extract all of its thermal energy. But the extraction process itself requires a heat pump, a device that moves heat from the cold object to a warmer reservoir. And as the object gets colder, the efficiency of the heat pump approaches zero, because the temperature difference between the object and the warmest available reservoir becomes the limiting factor. Each step of cooling becomes exponentially harder. You can approach absolute zero asymptotically, getting arbitrarily close, but never reaching it. In laboratory experiments, physicists have cooled gases of atoms to temperatures of nanokelvin, billionths of a degree above absolute zero. At these temperatures, the quantum mechanical behavior of the gas dominates. The atoms form Bose-Einstein condensates, a state of matter predicted by Einstein in 1925 and first achieved in the laboratory in 1995, in which a large number of particles all occupy the same quantum ground state simultaneously, behaving as a single coherent quantum entity rather than a collection of independent particles. These condensates display phenomena like superfluidity and coherent quantum oscillations that have no classical analogue. The universe at 2.725 Kelvin is enormously hotter than these laboratory extremes, but it is colder than anything else that exists naturally on the scales we have observed. No star is colder than the CMB. Stars are, by definition, hot. No planet surface, no nebula, no dust cloud in interstellar space is colder than the CMB. They all receive CMB radiation and equilibrate at or above 2.7725 Kelvin. The CMB is the universal floor, the baseline temperature from which everything departs upward. What happens as the universe continues to expand? The CMB temperature continues to drop. The relationship is simple. The CMB temperature is inversely proportional to the scale factor of the universe, the factor by which all distances in the universe have expanded. The universe today is about 1,100 times larger than it was at recombination, which is why the CMB temperature has dropped from 3000 Kelvin to 2.725 Kelvin by a factor of about 1,100. As the universe expands by another factor of 1,100, which will take tens of billions of years, the CMB temperature will drop to about 0.025 Kelvin. The thermal floor of the universe is not fixed. It is falling, slowly but continuously, as the universe expands and its ancient light grows ever colder. In the very far future, the CMB temperature will approach zero. The universe will be essentially at absolute zero. Not quite there, never quite there, but so close that the distinction becomes physically meaningless. The stars will have long gone dark, the white dwarfs will have cooled to blackness. The black holes will have evaporated over timescales of 10 to the 100 years. And in a universe that vast, that old, that cold, there will be no temperature gradients, no free energy, no complexity, no life. Just an almost empty, almost 0 Kelvin, almost perfectly dark universe, expanding forever toward an absolute zero it can never quite reach. That future is real. It is the inevitable destination of the universe as thermodynamics allows it. And the fact that we are not there, the fact that we are in a universe with stars still burning, with a CNB temperature of 2.725 Kelvin rather than 0.1 Kelvin, with thermodynamic gradients still large enough to sustain the complexity of life and thought, is not an accident. It is a consequence of where we are in cosmic history. We are in the middle of the story, not at the end. The universe is still young enough, still hot enough in its local concentrations, still cold enough in its background that the engine runs. We are asking the question because we are inside the window where the question is possible to ask. There is one more thread to pull, and it is the strangest one. We have talked about temperature as a property of matter, about radiation as the mechanism of heat transfer in vacuum, about the CMB as a relic from the beginning of time, about the thermodynamic gradient as the engine of life. But there is a deeper question lurking beneath all of this, one that the original question almost touches without quite reaching it, and it is this: why does time have a direction? You already know that it does. You know this without thinking about it. A video of a cup falling off a table and shattering plays differently, forward and backward. Forward, the cup falls, hits the floor, shatters into fragments that scatter outward. Backward, the fragments leap together, assemble into a cup, rise off the floor, and land upright on the table. The forward video looks real. The backward video looks like a magic trick, an obvious violation of the natural order of things. You know immediately which direction is forward. And yet, this is the strange part. The laws of physics at the microscopic level are almost completely time-symmetric. The equations of motion work equally well in both directions. If you reverse the velocities of all the molecules in the room, physics would allow them to spontaneously assemble into a cup. There is nothing in the fundamental equations that forbids it. The reason the backward video looks wrong, the reason time has an arrow, is not because the laws of physics forbid the backward version. It is because the backward version requires an extraordinarily improbable configuration of all those molecules, while the forward version evolves naturally from a vastly more probable initial state. Well, BI, entropy, thermodynamic disorder, tends to increase, not because nature has a law requiring it, but because there are overwhelmingly more disordered states than ordered ones. Well, and random processes explore configurations with frequencies proportional to their abundance. The shattered cup is a high entropy state. The intact cup is a low entropy state. The evolution from intact to shattered is entropy increasing, moving from a rare configuration to a common one. The reverse evolution would require entropy decreasing, moving from a common configuration to a rare one, which can happen, but with a probability so vanishingly small that in practice it never does. This is why time has a direction. Time's arrow is entropy's arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. Now here is the connection to our question. For entropy to increase, for the arrow of time to point somewhere specific, the universe must have started in a state of very low entropy. And it did. The Big Bang was an extraordinarily low entropy event, a universe compressed to near infinite density, almost perfectly uniform, with all matter and energy in a state of nearly maximal gravitational simplicity. As the universe expanded and gravity sculpted matter into galaxies, stars, and planets, entropy increased. But the entropy increase driven by gravity is different from the entropy increase of a gas expanding into a vacuum. Gravitational systems actually have a larger available entropy state when matter clumps, not when it spreads. A universe of smooth gas has lower gravitational entropy than a universe of stars and black holes. So the universe is moving from low entropy toward high entropy by forming progressively more complex gravitational structures, a process that will culminate eventually in black holes and their subsequent evaporation. But along the way, at the particular moment in cosmic history where we find ourselves, the entropy increase produces something remarkable: stars. Stars are local entropy increasing engines in the service of a larger entropy increase. They consume nuclear fuel, converting hydrogen to helium, a process that increases entropy within the stellar interior, and in the process, they produce photons. Those photons carry entropy outward into space. Here is the critical thermodynamic accounting. The Sun absorbs no photons from Earth and emits a continuous stream of high-energy visible light photons toward Earth. Earth absorbs those photons and re-emits them as infrared photons. The energy is conserved. Earth emits the same total energy it absorbs, otherwise it would heat up without limit, but the entropy is not conserved. One high-energy visible light photon carries less entropy than several low-energy infrared photons carrying the same total energy. Earth is absorbing low-entropy, high-energy photons and emitting high-entropy, low-energy photons. The difference, the entropy gap, is what all life on Earth uses to maintain its ordered structures. The Sun is an entropy pump. It takes the low-entropy nuclear fuel stored in its hydrogen and converts it into high-entropy radiation, emitting that radiation into the even higher entropy sink of deep space. Life on Earth intercepts parts of this entropy flow and uses the entropy gradient to build and maintain improbable structures, cells, organisms, ecosystems, civilizations. We are not violating the second law. We are surfing the entropy wave. The second law is the wind in our sails. We go where the entropy goes, from low to high, and we use the gradient to do work along the way. The coldness of space is therefore not just a thermal fact. It is a thermodynamic condition that determines the direction of time's arrow locally. If space were at the same temperature as the Sun, entropy would not increase in the Sun-Earth system. There would be no gradient, no entropy flow, no available work, no time's arrow as we experience it in the context of life and chemistry. The asymmetry between the past and the future, the irreversibility of biological processes, the fact that you remember yesterday and not tomorrow, the fact that you grow old rather than young, is grounded, ultimately, in the temperature difference between the Sun and the cold void surrounding it. And that cold void is cold because the universe is old and expanded. We are 13.8 billion years into the expansion. The universe is cold. The background radiation has been redshifted from 3000 Kelvin at recombination to 2.725 Kelvin today. The direction of time, the direction you are reading these words in, the direction your thoughts are moving as you process these ideas is ultimately aligned with the expansion of the universe and the cooling of its background radiation. You are made of matter that was once in a star. The iron in your blood was forged in a stellar core that collapsed and exploded, distributing its elements across space. The carbon in your cells was built from hydrogen and helium in stellar fusion chains. The calcium in your bones, the oxygen in your lungs, the phosphorus in your DNA, all of it was cooked in stars and scattered into the galaxy before being gathered by gravity into the solar nebula, then the Earth, then life, then you. You are literally made of stardust. The cliché is not a metaphor, it is chemistry. But you are also, in a deeper sense, made of a temperature gradient. The arrangement of those atoms into a functioning nervous system, the maintenance of that arrangement against entropy, the information processing that constitutes your thoughts, all of it is powered by the sun and made possible by the cold of space. The sun without the cold would be useless. The cold without the sun would be lethal. It is the contrast, the 5,778 Kelvin against the 2.725 Kelvin, that makes you possible. You are asking why space is cold when the sun is so hot. The answer is, space is cold because the universe is 13.8 billion years old, and those 13.8 billion years of expansion have cooled the cosmic microwave background to 2.725 Kelvin. The sun is hot because gravity compressed hydrogen to fusion temperatures and ignited it 4.6 billion years ago. The contrast between these two temperatures, one ancient and universal, one local and stellar, is the engine of every biological process you have ever experienced or will experience. It is the engine of your metabolism, your heartbeat, your thoughts, and the thought that made you ask the question in the first place. The question answered itself. You are the proof that the answer is right. The immediate answer, space, has no temperature because temperature is a property of matter, and space contains almost no matter. The vacuum is not cold, it is empty. The question contains a false premise. The practical answer, objects placed in space reach very cold equilibrium temperatures, approximately 2.725 Kelvin, in the absence of nearby stars, because radiation is the only heat transfer mechanism available in vacuum. With conduction and convection absent, objects can only gain heat by absorbing photons and can only lose heat by emitting them. Far from any star, the only photons available are the cosmic microwave background, corresponding to 2.725 Kelvin. Objects cool toward that temperature. The astrophysical answer, the CMB temperature, is 2.725 Kelvin because the universe began 13.8 billion years ago in a hot, dense state and has been expanding and cooling ever since. The CMB is the relic radiation from the epoch of recombination, 380,000 years after the Big Bang, redshifted by the expansion of space from 3000 Kelvin to 2.75 Kelvin over 13.8 billion years. The coldness of space is not arbitrary. It is a specific number that encodes the history of the universe. The quantum answer, the thermal radiation spectrum, the Planck curve, is the consequence of the quantization of energy. Planck's discovery in 1900 that energy comes in discrete chunks, not as a continuous quantity, resolved the ultraviolet catastrophe and provided the correct description of thermal radiation. The specific temperature of the CMB is confirmed to extraordinary precision because the CMB spectrum is a perfect Planck curve. The thermodynamic answer, the sun is hot and space is cold, because that is the thermodynamic condition for the existence of complexity. The temperature gradient between the Sun's 5,778 Kelvin and space's 2.75 Kelvin is the engine that drives photosynthesis, metabolism, weather, climate, and every other process that constitutes the biosphere. Life is a thermodynamic engine running on that gradient. Remove the gradient and life is impossible. The cosmological answer: we exist now, during the Stelliferous era, because now is when stars exist, and the thermodynamic gradient is large. In the early universe, before stars, there was no gradient. In the far future, after the last stars have burned out, there will be no gradient. The window defined by the existence of stars, the window in which the sun is hot and space is cold, is the window in which life is possible. We are here because we are in that window. The deepest answer: the sun is hot because it is a gravitational machine burning hydrogen, a local hotspot in an ocean of cold produced by gravity's ability to organize matter into nuclear furnaces. Space is cold because it is the baseline state of an old, expanded universe. The contrast between them, the temperature difference of more than 2000 Kelvin, is the most important fact about the thermodynamic environment of life on Earth. It is not the background condition of your existence. It is the cause of your existence. Every heartbeat, every thought, every word of this script, every moment of human civilization, thermodynamically powered with a difference between the sun's heat and the coldness of space. You were asking the wrong question. But the wrong question, followed far enough and honestly enough, reveals something extraordinary. The apparent paradox you started with, how can space be cold when the sun is so hot, is not a paradox at all. It is not a contradiction. It is not even a coincidence. It is the thermodynamic condition of your existence. The gradient between the two is not a problem to be solved. It is the engine that runs everything. The sun is hot, space is cold. You are the consequence of the difference between them. If that perspective, seeing yourself as a creature of a temperature gradient, a thermodynamic engine sustained by the contrast between a star and the void, if that perspective changes how you see the cosmos and your place in it, then this video did what it was supposed to do. Hit the like button if you want more of this. Subscribe if you want to be here when we ask the next question that looks simple and turns out to be a window into the deepest structure of reality.